So moving forward towards the next session of this day, and the topic for this session is numerical characterization of graphene-based polymer nanocomposites. And the speaker is none other than the coordinator of this FTP, Dr. Animesh Talapatra. So let me introduce Sir. He is an associate professor of mechanical engineering at Elitte College of Engineering with over 18 years of teaching and research experience. He holds a BE from NIT Agartala and MTech in Materials Engineering from BESU Shibpur and a PhD from IIES Shibpur. His expertise lies in advanced materials, molecular dynamic simulation, FEA, and graphene-based nanocomposites. With over 100 research publications, he has also served as HOD at MCKVIE, Senior Research Fellow at IIT Kharagpur, and guest faculty at Maulana Abul Kalam Azad University of Technology. We are really feeling privileged to get such an eminent academician as resource person for the second session of the day. Sir is already present. I can see him. Sir, please, you can start your session, please.
I am audible?
Yes, sir. Absolutely audible and visible.
Okay. So first of all, thank you for the brief introduction about me. And basically, we are focusing on the modeling and simulations. So I will try to avoid the experimental part because experimental part is very costly as well as is basically requires some special space, special equipment. So modeling and simulations is very helpful because before going to the fabrication of the material, if you know earlier what will be the condition, you can easily get the idea from the modeling and simulations. So I am sharing my slide initially. The slide is visible, madam?
Yes, sir. Now it is visible. But please go to the slideshow.
Okay, so first of all the participants for joining these sessions for across the India. So I am moving my slide. This basically numerical characterization graphene-based polymer nanocomposites. So we have seen all the presentations. That will basically few presentation is related to the experimental procedure, few will be the simulation based. But I basically focusing in my presentations is basically simulation based. And in my presentation contents, give the brief introductions, then go to the different simulation models. Then different simulation models is required to find out the property, and that property may be mechanical property, interfacial mechanical property, tribological property, thermal property, corrosion property, impact property, viscoelastic property. So I have to show how to find out that property using the molecular dynamics simulation, and also show the scope of work for latest models and which are basically coming in within few days. Also show few amount of experimental work based on the graphene-based polymer nanocomposite, and finally give a brief conclusion and future outlook. While starting these slides I am giving just about the different simulation experimental procedure. So, so you have to see that if the go to the tensile testing, initially you have to prepare the sample, then purchase the component, purchase the machine. It requires a much cost. But if you initially do the simulation, and simulation may be do by two way, either finite element or molecular dynamic simulation. So you have to do the tensile testing, FEM simulation as well as the molecular dynamic simulations. But the result will be different in FEM results and molecular dynamic simulations. These two results may be different from the experimental procedure. However, you get a early idea what is happening, as well as the heat treatment process. We know that the different types of the heat treatment process are available, and we can do the annealing, then tempering, hardening, different types of heat treatment. But as well as we can do the heat treatment in finite element, as well as the molecular dynamic simulation. So in the molecular dynamic simulations, there may be a much more complicated compared to the finite element simulations, but we get the much idea what is happening in the during the heat treatment process with at the atomic level as well as the bulk level. So this is basically my introduction slide, how the experimental work simulation works basically compare and get the idea what is happening within that material. This is very essential because experimental procedure is required much times as well as requires some money. Once is the machine, but if you go to the simulation, you get a much idea, but result will not be same. In experimental result, definitely different from the simulation result. However, you have to get the idea what is happening within that materials. And already you know that at the atomic level property and the bulk level property, these are the totally different. If you go to the graphene or CNT, we have to see that the Young modulus is much higher. If you go to the simulation, MD simulation or molecular dynamic simulations. This is just introductions about what is basically experimental finite element and molecular dynamics. Molecular dynamics require much time compared to the finite element simulations because we have to set up the atoms from bonding and to set up the crystal and unit cell. Then that means then we have to develop the different properties help of different equilibrium situations. So for example, NBT and different basically we have to set up the equation so that we get the property as like of that materials. So this molecular dynamics simulation is nowadays popular because you can get an idea at the atomic level. So I'm moving on the next slide. So going to the material regulations. So we have human simulation has seen that different regulations from stone age to steel age, then silicon age, then we are living on the carbon age, and we are going to the carbon age different nanometers. Carbon-based nanomaterials may be different types. It may be graphene, CNT, fluorine. So if you see a discovery, that initially graphene was discovered, then carbon fiber, then fluorine, then carbon nanotubes, and ultimately 2004 the graphene was discovered. And this is discovery is a basically simple uh, cellotypes. From cellotypes, they have discovered the graphene. Two scientists, one will be the Konstantin Neposelov and Henry James. They basically discovered this in 2004, and for that they got the Nobel Prize in 2010. So this is a new revolution in material industry, graphene. Nowadays, it is known as the king of all materials because its property is so powerful compared to the steel or other material. You can apply that graphene in different applications. Nowadays, in purifying water, bulletproof jacket, lubricant, even sports application, electronics application, wire application. So here nowadays they apply the graphene. Graphene is nowadays is more vital in you have changing the world with the help of the graphene. You have to see that the graphene nanopowders can be used as a best lubricant. So these are the material regulations that will give an idea how the new material is coming in the for bulk critical nanomaterials. So nano concept already you have to know that the nano concept. I think everyone know the nano concept. So the dimension depends. So if it is the 10 to the power 9 meter, then it will be the nanometer. So nanometer is basically you can say the nanotechnology that will be depends on nanometer, which size must be the 10 to the power 9 meter. And in atomic scale, carbon graphene they call it that nanometer is 10 to the power 9 meter. So if you go to the different scale, the atom level, it is the atomic scale, then it will be the micro scale, then macro scale, then we have to apply in the structural application is the structural scale. So this nano dimension is very important for during the simulation of MD simulation or any model development because you have to develop the model in atomic level and that must be within the nano range. Carbon-based nanomaterials. So already everybody know the graphite. Graphite is basically stacking of different graphene layer. So graphite is basically 3D. Then 1D will be the basically known as the view. 2D will be the graphene and 0D is the fluorine or buckyball. So we have to apply different types of nanomaterials in different applications. Out of this nowadays is very popular is the graphene. So graphene is also known as the king of all material for its extraordinary. I've said that there is a discovery of the different carbon-based nanomaterials. That fluorine was discovered in 1985. then is single nanotube in 1991, and multi-wall nanotube is 1993, and in 2004 the graphene was discovered, and this discoveries is give a new revolution in the material industry. And two scientists, Andrew James and Konstantin Novoselov, basically discovered this, and for that they obtained the Nobel Prize for the thinnest and strongest form of. Now we are moving to the graphene. So graphene is basically sp2 hybridized arrangement and strong sigma bond as well as outplane pi bond, also known as the semi-metal, and shortest distance is 0.142 nanometers. Odd angle will be the 120-degree. Thickness of the graphene is most important whenever modeling any graphene base. This thickness is very important. The thickness of the graphene is 0.335 nanometers. From this table, see that different property of the different nanomaterials, and out of this graphene has a significant long modulus is 1000 gigapascal, strength is 130 gigapascal. As well as shear modulus and bulk modulus is also better. So what will be there? You have to concentrate young modulus, because in our structure, young modulus is most important for designing. It's so strong that Professor James Holmes in Columbia University said that graphene is so strong that it will take an elephant balanced on a pencil to break through a sheet of graphene. So from that we can say that it is more than 100 times the strength of steel. So it is so powerful in material industry. You can change anything, either different applications. Nowadays, the automotive sectors are playing vital role in the application of the graphene. So graphene types, as graphene, we are saying that graphene may be also different types there. If it is one layer, then it will be known as the pristine graphene or monolayer. If it is 1 to 3 layer, then it will be the very few layer graphene. If it is 2 to 5, then it will be the few layer graphene. If it is 2 to 10 layer, then it will be multi-layer graphene. And if it is more than 10 layer, then we can known as the graphene nanoplate. So nowadays, basically, pristine graphene is more costly compared to the graphene nanoplates. So most of the institute research, they are using the graphene nanoplates. But pristine graphene is much better compared to the graphene nanoplates. So you can see that the 3 million layers of a graphene in 1 millimeter of the graphite. So you can see that 1 millimeter graphite consists of 3 million layer of graphene. So the graphene layer basically a significant role for enhancement of the property. And if you adding the pristine graphene in the any polymer matrix, that gives a better property. There must be some merit and demerit of the pristine graphene. I've written here. So already it is gives a excellent mechanical property, high electrical conductivity, extremely high surface area, high thermal conductivity, and optically transparent. That's why we can apply in transparent bulletproof jacket or transparent uh, glasses in graphene. So it can penetrate, do not penetrate the bullet also. It is also antibacterial property. So there must be some demerit also. That demerit is basically we have to overcome so that we can easily apply the graphene in our daily life. So the different form of the graphene, we can generate different forms, and for example, singular graphene, graphene oxide, reduced graphene oxide, graphene nanoplates. So you have to get the different property you develop from graphene. So ultimately, the singular graphene gives a better property. You have to see that the Young modulus is nearly 1 terapascal, tensile strength is 130. So if you want try to get the single layer graphene, though it is much costly compared to other. So whenever we have to apply the single layer graphene in any practical application, definitely property enhancement. So history of the nanocomposite. History of the nanocomposite, that means it is not ancient age. This application is also available to changing the glass, and the gold nanoparticle of different sizes used to produce different colors in glass. So this concept is now new day. It is available in the ancient age also. So, but they apply this concept in different. But this concept is also available in earlier days also. Graphic applications. So this applications is now popular in current field using the graphene based applications. So there is a huge number of applications. I cannot speak of it, but our focus on the composite. The graphene is improving the composite property. Basically, the focus of my presentation. Also, the modeling simulations, how we improve the property. I am not giving the experimental procedure, how the property is improved. I am showing in my presentation only modeling and simulation. So, nanocomposite application is first used in the automobile sector. So nylon timing belt cover, that was in 1991. First nanocomposite was introduced. And it is also introduced in the automotive sector for developing this timing belt cover. But nowadays, these nanocomposites are coming in different fields. Nowadays, this is most important. If there is a diabetes patient, if there is a body sugar level, thing, so these types of the material change. Suppose the person is increasing, so the contacts are also changing, and that will give the identification. This person sugar level is high. So nowadays, this nanocomposite is used as a contact lens for the diabetes patient also. Even in bulletproof jacket, and that will be the transparent bulletproof jacket that research is going on. So graphene-based polyurethane ballistic applications where bullet cannot penetrate, even it is transparent. Nanocomposite, we know that tennis ball. Tennis ball is the one of the example of the nanocomposite. So we use the rubber ball, but nanocomposite this tennis ball is basically gives a better viscoelastic property. Even in biomedical applications, hip joint, there will be also application of this nanocomposite. Also the self-healing applications, nowadays this nanocomposite is also used. Nanocomposites or graphene-based nanocomposite nowadays they apply in different fields, not only automotive. We use in the medical field, using sports and the defense applications, uh, medical. So there are the numerous number, different numbers of applications nowadays is coming out in nanocomposite graphene-based. So just I am going to the basic composite materials. So already know all the participants what is composite. Composite is basically the combined of two these. One is the matrix, another one is the fiber, one is the reinforcement. So this may be continuous space, less strips, quicker fits, and reinforcement may be discontinuous space, more stiff, stronger. But if you go into the nanocomposite, this is totally different. Matrix will be the same, but what will be changing? Reinforcement. There must be reinforcement will be the nano range. That means 10 minus 9 meter. So this nano reinforcement, if you add it, then it will convert to the nano composite. So this is basically composite and nano composite. Nano composite reinforcement size must be nano range. As we are basically working on the carbon based nano composites. So uh, we are basically most of the automotive sectors are using polymer nano composites. In my presentations, I focus on the composite, graphene based. So this nanocomposite, one of the family of the is polymer nanocomposite. Nano reinforcement will be fluorine, carbon nanotube, graphene or polymer matrix may be plastic, elastomer, rubber. Elastomer with maybe two types, most of them are plastic. So this will be basically the basic classification of the carbon-based polymer nanocomposite. And we are focusing on the basically the nano reinforcement because we have to adding the nanofiller or nano reinforcement to generate or develop the nanocomposite. So it may be fluorine, it may be carbon nanotube, it may be graphite, it may be graphene. So in my presentation, I will focusing mainly on the graphene.
Sir, sorry to interrupt you. Can you
Oh,
hear me?
yes.
Actually, sir, your voice is breaking. Maybe it's a net issue. Net issue, or I think
Oh,
your.
now it is clear.
Yes,
Hello.
now it's clear.
Okay, so characterizations of the nanocomposite, and that may be experimental way or simulation way. So experimental way, different equipment, there are nano indentations, dynamic mechanical analyzer, scanning electron microscope, transmission electron microscope, and force microscope. Complex simulations, basically we are focusing on the molecular dynamics simulation and finite. So experiment simulations, basically we are using the abacus. Three body will be available. One will be the representative volume element, unit cell modeling, and this is the new is the object oriented. I am basically focusing on the molecular dynamic simulation. In that element simulation, we are focusing this object is very popular nowadays because we can get the properties of the material from a microscope. If you generate the structure of any composite or the microscope, you can show the property of that materials by using the object. So this is the new research area for the property. The molecular is also available, but the what much times and it is much cost. This is the basic idea about the different simulation. So if you go to the bell and it's the molecular dynamics simulation, if further if you reduce the size, then it is the quantum mechanism that will be the Schrodinger equation. That is the DFT we have to use. It's a different simulation method. But above quantum mechanics, that is the molecular dynamics simulation from the Newton's equation of the motion. So, otherwise, if you moving further in more distance in meter range, then it will be the continuum. You have to use the finite element. This basically different nano, micro, meso. This all together we are basically known as the multi-scale modeling of the simulation. So multi-scale modeling of the simulation, that means you can do finite element, you can do the molecular dynamics, you can do the DFT. So that is depends on the length of the size of that model. So for that particular, if there is a size is more, then more simulation time will be required. If size is less, then that. This is basically the nanocomposite model. Already I have this slide. One is the molecular dynamics simulation, another one is the finite element simulation. So molecular simulation, that simulation that so
Uh,
wherever
Sir, sorry for the interruption. Again, your voice is breaking and not clear always.
now
Yes. Actually, sometimes it's absolutely clear and sometimes it's not audible at all.
maybe changing of
Again, it's breaking, sir. Voice is breaking. Uh, yes. Can it be any headphone issue or anything like that?
no explanation.
Sir,
There
you
may
may off
been
your
some
video so that it will be maybe your net will get more
yes,
powerful or
there may have been some bandwidth issue, I think.
Yes, net issue, I guess. Bahar, is it possible that sir will leave once and rejoin? Can the situation be better?
Now, madam, this is
This
now it is
may have
situation.
been
No, sir. So your
Hello.
voice is breaking.
Oh,
one of your camera, then just proceed through PPT. Then we will be checking the audio. It is coming clearly or not.
Okay, sir. You carry on. Okay, let's see.
okay. Now these finite element methods, one PVC, then is the object oriented, and the OF. So OF2 is basically nowadays very popular because we can find out the property using the microstructure. So in OF2, what will be happening? Initially, we have to import the microstructure and then identify the phase, and after identify the phase, which will be the matrix, which will be the reinforcement, then we have to give the property of that. For example, you have to identify the graphene, and you have to identify the matrix or any polymer. Just input the value of the matrix property as well as the graphene property. Then after putting the property, then you have to create the mesh. That means the skeleton will be generated, and with the help of 3D skeleton, you have to generate the mesh. After mesh created, then we have to apply the equation and boundary conditions. So applying the equation and boundary conditions, we have to go to the analysis or solve. So there will be the two options there. If this is the elastic region, then you can easily find out the property from the OF2 software. But if it is the plastic region or failure region, there is a certain techniques there to find out the property. First, what will be there? You have to get the off mesh details and you convert into the abacus INP file. Then what will be there? You input that INP file in the abacus. Then you have to analysis get the. There will be the two way. Elastic region you can easily find out from the OF2 software, but if there is a plastic regions, then you have to go to the abacus to the INP. So these are the two way you have to find out the property from microstructure, find out the ultimately property. So no need to do the sample design or anything. You can get everything from the microstructure. So this is the new area where you can find out the net element analysis from microstructure. For plastic region, it is much easier. But if you go to the plastic region or failure region, then definitely you have to follow the file and find out the. So we are now moving the molecular dynamics simulations. So what will be the molecular simulations? There will be the three models. One will be the concentrated, the layer model, and artificial model. So concentration model is basically the peak of. So you have to get the different percentage. For example, 1%, 3%. We have to get the 40 from the concentration model. But if is there is a stacking or sandwich model, for example, formation model or model, so you have to go to the layer model. And then is the interfacial model. This is the open model by which you have to find out the interfacial. For example, find out the tribological property, find out the thermal property. So this interfacial model is very helpful. After getting develop the model, we have to go to the model equilibrium state. That means you have to develop the model as like as the original material. The water particle model. So water has 40 centigrade 1 gram per. So you have to develop the model. Uh, develop model will be the similar as the water pump. So this is more important. Go to the dynamic. After the model stage, we have to develop the functions. And in productions, what is the equilibrium condition and non-equilibrium condition. So you have to run the equilibrium condition analysis or non-equilibrium condition analysis. So in that way, you have to develop the FEM model, MD model, so that you get ultimately the property of that model. There are definitely some basically parameter there: temperature, pressure, force field, assemble, cut off distance, time step, simulation running time, strain rate. So these are the important parameters are required during the development of the model. So we have developed a concept model, layer model, artificial model to find out the different properties. In coming slides, I will show all the things how to find out the property using the different models. So this is the Material Studio software where different tools are available to develop the different models. So at first, what we have to draw the structure or put the structure. This is the beginning. For example, you have to develop the water model. So there must be hydrogen and oxygen. So initially you have to draw with the tool oxygen and hydrogen. You build the options. There you develop the crystal. After you develop the crystal, you have to go to the construction model. So in construction model, it definitely it may be concentrate model, layer model, or interfacial model. So when the model is developed, then you go to the equilibrium stage. So equilibrium stage is basically heart of the MD simulation. You can
Sir,
say everything is that.
sir, sir, you just do something. Please, you turn off your video and only let the slideshow on.
Okay, okay,
Slideshow should be going on, and you just please turn off your own video.
okay. I'm sharing. Right. Slide is visible.
Not yet. Yes, yes, now it's visible.
Okay.
Just go for the slideshow.
So there will be the
Yes, 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 sir.
so the model equilibrium conditions. Ultimately, you have to develop the model using the different stages. That means NBT, NBT, then NV. Different assemble you have to use, and after that, a production stage will become. In production stage, what will be their different first site module available. So in module maybe a cast module, foresight module, different application, different module can be used to find out the property. So this is the basic guidelines about how to find out the property. Now we're moving the graphene model development. So there is a certain criteria to develop the graphene model. So in the literature study, it is seen that length to weight ratio must be standard, so that it must be gives the standard property of the graphene. So you have to see that the after 30 length, so length to weight ratio is nearly 1. In that case, the graphene will get the 1 terapascal. So you have to develop the graphene length in width in such a way so that its ratio must be 1. As well as in thermoplastic polymer or polyurethane, there must be a number of not take the number of mass standard yeah, or thermoset polymer. Thermoset polymer, there is a cure condition or curing agent there. So you have to initially develop the triangle model of the cured structure. The few guidelines how to develop the graphene or polymer there so before developing the nanocomposite. So model selection of the property. So there is the concentrate model, layer model, and interfacial model, and each model is the different. For concentration model, we know the weight percentage, volume percentage. For that is used for the mechanical tribological property. Layer model that will know the uniform dispersion or agglomerate. And that is very helpful to find out the mechanical, thermal, and tribological corrosion property. And interfacial property, that means some void conditions or some in the box, if you see that there's some empty place there. So this interfacial model is basically a nano reinforcement effect on the interfacial property, that is thermal, tribological, and corrosion property. So these three models are very, very important to develop the nanocomposite and to find out the different properties. So this is the constructions, how to construct the different nanocomposite. If you go to the construction option, or there must be a two criteria. One is the crystalline material, another is the non-crystalline material. Already you know that the composite material is the non-crystalline or amorphous material. That means we are developing graphene-based polymer nanocomposite. Is definitely amorphous or non-crystalline material. So you have to see that in the softwares, there you have to adding different weight percentages of the nano reinforcement within matrix, and you have to give the density of that material as like as the real material density. So if the real material density is 1.3, then you have to input that. You are reading the defined weight percentage and run the simulation, you get the nanocomposite material at the defined weight percentage. This is done with the amorphous cell because nanocomposite or composite material is the amorphous, so you have to go this amorphous cell. But it's not non-crystalline. So, for example, silicon or silicon-based nanocomposite or nanoparticle-based nanocomposite, other nanocomposite cases we have to go to the crystalline build crystal option. So this is basically the construction model that is basically for weight percentage effect. You can give this construction model. But if you go to the laminated conditions, you have to go to the build layer options. But if there is a packing option, that means you are adding some water polymer material. You are adding something within the carbon nanotube. So what is the packing condition? So this is the packing model. Is also done by the amorphous because this is also a composite material. So with that, you have to develop the packing model. That is very important. That is the confined layer or built layer model. That is laminated composite. You know that the laminated composite. So in nano level, we also develop the nano composite laminated conditions. So built layer option is available to find develop the nano composite at the laminated condition. So ultimately, this is the guidelines. The build crystal that may be done by the crystalline material, non-crystalline material. Amorphous crystalline material means done with the visualization module. And type of the nanocomposite, it may be particulate mixing or laminated conditions. If it is particulate mixing, go to the packing conditions, concentrated models. If it is the layer model, with the help of the layer. Last is very important, property calculations. You have to find out the physical property, mechanical property, thermal property. That property calculation is depends on the force field, and force field is the heart of the molecular dynamics simulations. Different force field is available. Some force field is the reactive force field, some force is the non-reactive force field. Reactive force field, that means you have to breaking any bond. Suppose you have to break the any silicon rod or graphene layer. So that the breaking force field is there. That is the reactive force field. Non-reactive force means you have don't break the material, just find out the property. That is will be the non-reactive force field. So for example, foresight. Foresight is basically the non-reactive force field, but Gulf, whenever impact force application or bullet application, we have to apply the foresight mode. So this molecular dynamics simulations process initially build the crystal model of the reinforcement, build the crystal model of the matrix, then build the composite crystal, then done the geometric optimization or energy minimization. That is volume reduction. Because whenever you mixing this, that material is the high energy state. So you target to reduce the energy so that you get the accurate material. So geometric optimization is done, volume reduction. Then you have to do the molecular dynamics run so that you get the density of that material. When you have get the everything, the density, everything, temperature, everything, equilibrium condition, then you move to the property calculations. After property calculations, you can do anything. Either you have to find out the interaction energy or damage analysis. So, property calculation, you have to do many things for finding the different property. So, this is basically the guidelines how to simulate the composite simulation. So, these are the tools are available during the mechanical property calculation. That tools are very important because you have to set up every code within the software. So that will some tools are default value is available, but you have to change. Most important is the tasks because the tasks sometimes geometric optimization, dynamic run, mechanical property calculation. You always move one by one. So these tasks that means what you have to do now. And this is most important. You have to go to the different equilibrium conditions, pressure, temperature, because ultimately you have to get the equilibrium conditions. So the model will get the exactly at the real conditions. So you have to go different equilibrium conditions by setting the different tool. So graphene based polymer nanocomposites. Here I am showing that Initially, you have to develop the graphene, also develop the polymer. Then you mixing with the help of concentration model. Then you go to the energy minimization. Energy minimization supply kinetic energy under LVT symbol, because you have to apply different assemble to get different conditions. So supply kinetic energy under LVT symbol. Then better quality structure under annealing. So annealing, you can say one types of the heat treatment process, so that there you have to remove the void or anything within the material. So you have to do the annealing process also. After doing the annealing process, you develop the stress-free structure, because after doing the internal stresses will be generated. So you have to remove the stress-free structure with the NPT symbols. When this is developed, then you have to go to the property functions. So calculate the property that will gives with the help of that software. Now I'm moving one by one and different property. First, I'm moving the mechanical property. Modeling simulation of the graphene-based nanocomposite. So nanocomposite enhancement of the mechanical property, that means stiffness improvement, strength, young modulus, fracture toughness, resistance, formability. So this is one of the example, the Rice University, they have developed a bulletproof glass, where the bullet are basically don't penetrate the glasses and it is transparent. So this is one of the functions of basically graphene-based nanocomposites, and this now graphene is so strong that it resists the bullet also. So if you enhance the property of this all mechanical, need something. You have to changing the graphene parameters. You have to change the aspect ratio of the graphene. You have to change the orientation of the graphene. You have to change the degree of graphene, weight percentage, then the shape of the graphene, also numbering layer of the graphene. Also, if you do the functionalize of the graphene or molecular weight change of the polymer material, that will be basically few parameters by which you can improve the or enhance the property of the mechanical. So initially, if you change this with the simulation, then you can change the property of that. And ultimately, what is the achievement? Improvement of the structural design. So you can develop a structure which is gives a better conditions. So this is basically the procedure by which you enhance the property as well as enhance the structure. So we have to do some simulation works about the graphene-based epoxy. We have made in different weight percentage, and we have to see that there is a improvement. So from the curve, you have to see that after 5 or 6% there is an improvement of the Young modulus. Then further, there is a tendency to decrease the property. So Young modulus initially increase after addition of the 5, then decrease. As well as if you go to the shear property, you have to see that the shear property is increasing as well as decreasing. So the adding of the graphene, we can find out the weight percentage effect to the mechanical property. So we can easily identify in which weight percentage will get the best mechanical property. For running this parameter, we have to set up this simulation parameters shown in simulation in other slides. Which is the compass force field, energy minimization is 6,000 steps, kilogram NPT, and different parameters you have to set up so that you get the accurate structure. So this is the one of the work in which we are changing the cities and create the enhancement. And this is the this was the concentration model. Now is moving the layer models. So it may find out the property enhancement in different condition. Either it will be the dispersed condition or agglomerate condition. So as the graphene is a nano powder, if you're mixing with the polymer, will be much more agglomerated. So agglomeration may be either dispersed. We have to use the ultrasonication methods to disperse the agglomeration or remove the agglomerations. So the nanocomposite, some composite will be the agglomerate condition, some will be the dispersed condition. So this effect you can find out the which is the better by using this layer model. So we have to see that the dispersed condition, agglomeration condition, dispersed condition gives the better property, because graphene uniformly dispersed on the matrix gives the improved property. In experimental procedure, use the ultrasonication method to do the dispersed condition. This at the simulation way you can easily identify which model is better. Is either it will be the dispersed condition or agglomerated condition. This is very important, interfacial mechanical property. So already you know that there is no instrument available till now in the world matrix reinforcement. So one of the methods simulations. So molecular dynamics is the one of the playing the major role in the find out the interfacial mechanical properties. Similar way, we have to use the interfacial model and pull out the graphene from the matrix so that you get the property of the interfacial strength or interfacial forces. So one is known as the cohesive model. That means this will known as the normal model or cohesive model. Another is known as the pull-out model. So there will be the two models that are using to find out the interfacial property. And one of the work that is done using the object-oriented finite element and molecular dynamic simulations. So we developed the graphene-based nanocomposite or thermoplastic composite and find some basically develop the microstructure. With the help of microstructure, the object find out the as well as we use the molecular simulations and find out. You have to see that in experimental procedure, nanocomposites are 0.04 gigapascal. In object element, it is 0.204 gigapascal. But if you go to the molecular dynamic simulation, it is much higher. So you can see that the molecular dynamic simulation gives much higher compared to the finite element methods. Because finite element methods is nearly the experimental value, but molecular dynamics simulation gives the atomic level property. It is always coming much higher compared to the real material. But what is the advantage? You can get uh, the idea about that material. So these are the few publications in mechanical property calculations. So one of the thermoplastic which all are the SCA journals, composite interface and molecular simulations. So the mechanical property enhancement we have SCA journals like improvement. Now I'm moving from the tribological property because these tribological properties are playing much better role nowadays. So using the molecular dynamic simulations, you can also find out the tribological property. So already you know that the graphene is basically king of all material. Thermoplastic polyurethane is the third generation. So mix these two, then you get the next generation polymer nanocomposite for tribology. So I am not going to show the experimental stuff. I will show the molecular dynamics. Molecular dynamics, there will be the two model there to find out the property. One is the plate model, there will be the rod model. Okay, find out the coefficient of friction. This rod model find out the abrasion rate. These two models are developed with the help of the confined non-equational shear situation is required. Find out this model with coefficient of friction. So there will be the two simulation, interfacial model and layer models. So interfacial models, we have to see that the rod and layer model, there is a tool with the simulations with the different properties of the nanocomposite, coefficient of frictions as well as the abrasion rate. And in this study, we have to see that after 3% the property will be decreased due to the agglomeration of the graphene. Also, we get the effect normal load and sliding velocity using the two models. So, increasing the normal load, both value of coefficient and frictions and OR are decreased in friction model. Increasing of the sliding velocity, both value of coefficient of friction OR are decreased in OR. So, you get the idea from different coefficient OR from different. These are the publications. One will be the Tribological International Journals, that is 6.9. The Saja journals related to the tribological applications. I'm moving the thermal property because I have the few work is done related to the thermal property. Because in polymer material, glass transition temperature is very important. So we have to find out the glass transition temperature by MD simulations. We initially develop the model and find out the fractional free volume, and we develop the fractional free volume versus temperature, and we have to get a point where this curve is changing, and that point is basically indicate the glass transition temperature. So using the MD simulations, we can easily find out the glass transition temperature of the polymer nanocomposite. Now I'm moving to the corrosion property because this is the new area where you can find out the corrosion property of the nanocomposite, and coating inhibitor or coating you can find out the property by interaction energy. So initially the find out the total interaction energy, then individually you have to find out the interaction energy. And subtract that, then you have find out the interaction energy of the surface of inhibitor. So in the way you have to find out the coating, or you applying some layer on any surface, iron surface, anything. So which layer will be the much better, or which coating will be the much better? You get an idea about the property using this simulation. Now is most important is the impact property, because nowadays this simulations is more popular to impact analysis. So already know that the impact test of the high thin polymer has revealed a new area. It gives a much high specific energy compared to the other conventional barrier materials or steel or aluminum, anything. So in that case, graphene is basically thin material which thickness is 0.3. So if you apply the graphene in ballistic applications or ultra thin applications or uh, OMD simulations basically give an idea about the this polymer nanocomposites. So already you have to see that the graphene is the high young modulus, high strength, and low density. So it is stronger than steel. So in ballistic applications, graphene plays a very important role in coming few days. Simulation procedure, how you do the simulation impact procedure. So we are using the LAMP software and use the OB2 for visualization. So LAMP software is basically helpful because there are various reactive force field there. I've said that reactive force field are very important to bond breaking applications. So ERIBO is one of the reactive force field that is available in the LAMP software. So we have to use this LAMP software to find out the impact. There are certain steps there to find the impact. Actually, the model specific component is given geometry of the model geometry, and fix the fluorine above the graphic. So we have to put the fluorine or the then what or so so that the graphic or when they get a velocity, then you give the velocity on the effect in particular constraint so that effect on the graphing sheet. Do the simulations, and we have to put in the force field because bond breaking is there. And relaxation temperature range is 1 Kelvin to 800 Kelvin. Impact velocity is 4 to 10 km per second. So after pollution, we get the which graphene sheet is better. One is the single layer graphene sheet, the double layer graphene sheet, or is the triple layer graphene sheet. During the simulations, you have to set up different parameters, and we have to do the NBT assembles. Time step is 0.7. Simulation is 5%. And under the NBA assembles, time step is 0.05 seconds. Simulation time is 20%. Potential force field we have to use because this is a on breaking force field. Showing a this is basically the different coloring board impact on the graphene sheet. One is the single layer graphene sheet, this is the double layer graphene sheet, this is the full layer graphene sheet. So the we have to take in the set coloring. C60, C40, C720. This is the number of carbon atom. C60, that means 60 carbon atom. So there is a standard length of the single layer graphene. You have to impact each pole on the graphene sheet. And there is a certain parameter there: initial velocity, elastic limit velocity, and there is a residual velocity. Residual velocity, that means ball then pass away the graphene sheet. Elastic limit, that means it is not passing any impact on the surface, or it may just moving. This is the conditions you have to find out during the. This is one of the simulations that is done. It is visible for everyone. So this is basically impact the graphene sheet, not drag the graphene sheet. So if you are increasing the velocity of that ball, then easily drag the graphene sheet. So increase the velocity of that, so that it can break the graphene sheet. So in my works with single layer graphene, double layer graphene, triple layer graphene, we impact the that ball impactors 4 kilometer per second, then 4.6, and then 5 kilometer per second, and 6.6 kilometer per second. So 6 kilometer per second it break the graphene sheet. As well as in case of the double layer, we apply the 8 kilometer per second, then it break the graphene sheet. And in case of the three layer, it's a 10 kilometer per second, it break the three layer graphene sheet. So it is also find out the residual velocity. Already we discussed what is residual velocity in the earlier slide. So in that way, you have to find out the residual velocity, impact velocity, when it is breaking the graphene sheet or not. So these simulations, easily you can see what is happening. So 6 kilometer per second, just break the one layer. 8 kilometer per second, you break the two layer. And 10 kilometer per second, it break the three layer. So in that way, you can easily identify. And this is applications where it is application nowadays in space application, because space we have to space shuttles, or it is moving in space. So various particles are hitting on the space shuttle. So the velocity is much more higher. So the molecular dynamics simulations, we can easily understand what is happening. So this molecular dynamics nowadays is very applied in the space applications for the hypervelocity impact. So from the result, we have to see that the different layer specific penetration energy, and we get that the three layer graphene gives the much higher specific energy, as well as the fluorine size. You can see 60, C180, C220. You have to see that there will be the diameter size and ballistic limit will be decreasing. If it is basically the C24 is ballistic limit, C60. So we can get an idea from the few research articles I found using these MD simulations to find out the equation. This is very popular because graphene polyurethane impact property of the 2019. So they are using same way in project and develop the different layer of polyurethane and do the that simulations to find out the velocity is the impact. So I'm moving on. The next topic is viscoelastic property, because graphene-based thermoplastic polyurethane is gives the viscoelastic. Because now we have to know that the viscoelastic, that means there will be the elastic and plastic both property are. From the figure, you have to see that we are using the rubber ball as well as the tennis ball is basically the polymer nanocomposite. So from the figure, you can see that there is a loss energy, smooth loss energy, but in rubber ball there is a much more loss energy. So we have to find out the storage energy, loss energy, as well as that can then value from the MD-based simulation study. What will be there? You have to do some simulation step, find out the DMA testing, because dynamic mechanical analyzer is used to find out the loss energy, storage energy, as well as loss tangent, and that will be very costly for DMA testing. Go to the dynamic testing, the molecular dynamics, you can easily find out these types of. But what you have to do, initially you have to develop a building amorphous using the concentric model or layer model or uh, other models. So that models, you have to do the program for dynamic run, and then after that you have to do the shear strain measurement. And there is in the softwares, what will be there? The Perl script is generated. It is very helpful to party. So using that data, you have to do the function test. Function test, you have to do some Python script is available to do the compression test and generate the data. This data is very helpful to find out the store modulus, loss modulus, loss tangent. There is a Python script there. This Python script is basically find out the storage modulus, loss modulus, and loss tangent, that compression data. So these are the few steps in molecular dynamics simulations by which you have to find out the viscoelastic property. And these are basically mainly used for the thermoplastic polymer. So these are the procedures where you have to develop the different model. This is a PUTPU. This is the 1%, percentage, 4%. You see that some agglomeration. So when there is some agglomerate condition there, definitely the decrease of property. So in simulation, you can easily find out which weight percent is suitable for your applications. So initially, we develop different models, and we apply the Perl script to find out the shear rate in non-equilibrium simulation. And after getting that, we use the Python script. Python script used with the storage modulus, loss modulus, and loss tangent. So that is basically not complete, because this data is getting from the software. Python script is available. Just input all the data in the Python script, then easily you can find out the parameter. So in that way, we have to find out the viscoelastic property of different materials, and that are basically gives the much more idea before you go into the dynamic mechanical analyzing test, because in experimental test, dynamic analyzer is very much costly. So as well as the sample preparations. Also, initially you have to prepare the 1 weight percentage sample, 2 weight percent, different weight percentage sample you have to prepare. After that, you have to develop the sample of the DMA machine, because there is a standard dimension of the DMA machine. And after developing the samples, then you have to test and getting the result. So it requires much more times. But if you go to the simulation, get an idea which sample is better for viscoelastic. So in the our study, you have to see the 3 weight percent gives the better viscoelastic property. So if you initially get the idea 3 weight percent is, then easily you can go move develop the 3 weight percent sample for DMA testing, not required to other sample. So it gives a less times to preparation of the sample. From the molecular simulation, you get an idea which weight percentage is preferable. Then you move to the prepare the 3 weight percent sample, prepare the testing of the 3 weight percent. But result will not be identical, because molecular dynamics simulation result is much more higher compared to the experimental. At least you get an idea or guideline which samples you have to prepare first. And there are definitely a portion of your cost or purchase of the machine. So these are the really helpful of simulations to get idea about the function of the system. So in the testing, you have to see the 3 weight%. This gives basically high increase the store modulus and decrease the loss modulus. In the temperature, you see that the loss modulus, store modulus is increase of store modulus, loss modulus. You have to get much more idea what is the effect of the weight percent. These are the new scope of work. You can convert the MD model to finite element model because molecular dynamics models are different compared to the finite element model. But you can convert that model to finite element model. So what is the procedure? It is nothing but you have to develop the model and go to the mesosite density function, then match the mesosite density function, then convert in Abacus. So nowadays in Abacus software, there is an option to input set model. So easily you can develop the molecular dynamics model and then it convert to the mesosite model. Then that model you can easily import in the Abacus software and then idea about the you can convert one more model for molecular dynamics. Result is much higher easily convert the model. So nowadays, these are much more popular. So it's possible. So then I am giving an application of the graphene based nanocomposites. So you know that there will be the 3 methods are available to develop the graphene based nanocomposite. One is the in situ polymerization, melt extrusion, and solution method. So in situ polymerization is a highly costly process. As well as the melt extrusion, there is the agglomeration happening. So one of the best method is solution method. So solution method, what is happening? Mixing the graphene nanopowder with the matrix and within the solvent. Ultrasound. So whenever you have to apply the ultrasound, what is happening? All the graphene respond and distribute similar things. Initially, TF solvent the solvent we mix the solvent, mixing them and do the ultrasonications. Ultrasonications, then the uniform dispersion of the graphene powder matrix. Then next we have to do the curing. Done initially the Beckham movement because there is a new air bubble there. To the Beckham movement, this air bubble will be removed. So after moving from the air bubble in the solution, go to the evaporation process. Evaporation process, we get the sample. And then we go to the hot press to get the accurate. So this is the method, solution method by which you get the sample of the nanocomposite. These are the basically the new testing sample is prepared for DMA testing as well as the cell testing. So DMA testing that will give the risk list storage modulus, log bones experiment that will be used for the young modulus preparations. Also, you know that the graphene based nanocomposite or rubber that will be the standard specimen known as the dog bone specimen, not like as the steel. So whenever you have to do the testing of the steel, there is a difference in operations. But if you go to the graphene based nanocomposite, the ones just mentioned there. that we have to do the testing of UTM machine as well as the dynamic mechanical testing to find out the property and compare the result with the molecular dynamic simulation as well as the finite element simulation. To get the idea what is result is better, you will get the better result to the molecular simulation. Because molecular dynamic simulation get a much atomic level property, and in the atomic level you say that there is no void or any defect there, so you get the much better property. But whenever you go to the finite element or sample situations, what will be there? Some defect will be coming in that property. Definitely the property will be different. So for reasons at the atomic level or molecular dynamic simulations, we get the much more higher value or higher property compared to the bulk material. Research area of the nanocomposite, there will be the two area you can say. One will be the related enhancement. There will be the special function. Special functions nowadays very popular. They apply self-healing applications in self-healing. Primary functions are basically enhancement of the different materials. So we have to apply different applications in the nanocomposites. So the conclusion outlook compared to the expensive nano experiment, simulation-based study can give a more suitable alternative method of clear initial. So already we get that concept to go to the nano experiment. For example, DMA testing or tensile testing required much time, sample preparation, cost of the machine. So that will leave the expensive for conducting the nano experiment. But if you go to the simulation-based study, you can do many things with the simulations. Is much more suitable to alternative to get the idea at the initial stage. That means which sample will give the better property. We can develop thousands of samples. Which sample with the property that can get from the simulation. But if you develop the thousands of samples in experimental way, it requires much time as well as much many cost, or that means required many things. So simulations basically helpful to conduct before the experiment. Also, due to the technical challenge in experiment level, MD simulation suitable for investigation of the load functions graphene polymer. So already I said that whenever we have interfacial property, till now no instrument is available. Suitable instrument is available to find out the interfacial mechanical property till now. So molecular dynamic simulation is the only tool by which you can find out the interfacial mechanical. Interfacial mechanical property, that means fiber and matrix in which that prisms is basically play a vital role in composite material. Simulations find out the gap between the fiber and matrix that will be connected, sometimes van der Waals bond or some bonds. There is interfacial region. That interfacial regions play a vital role in composite material, enhance the property of the composite. So this interfacial property can be done or can be identified by the molecular dynamics simulation. So this is the very important tool of the interfacial region. And graphene nanocomposites show the extraordinary property simulation result that can be applied in shell applications. Now it is in electric vehicle as well as then battery, EV battery. They are trying to apply this graphene-based nanocomposites because graphene is a better material in the battery application. And to know, get the knowledge how to protect the hypervelocity impact of ballistic protection or in the field of space applications, this hypervelocity impact can be done using these types of simulations. Already I've said that in space shuttle or any space applications, there is a different impact that may be hypervelocity, and that can be done with the help of that simulation. You cannot do experimental way to do this hypervelocity impact. So this MD simulations is This is the best simulation methods to find out the ideas. Percent is much more. So because of this expensive experimental study for hypervelocity, with this computer or any simulation is the ideal in this situation. So these are the softwares that are used in my work in the web software. This is free software. To the web software, open website. This web 3 is coming 3D. So this web software is done for the microstructure. So it's not software. So it is bits of console or bits of simulations. AMS is a free software. So if you want more simulations, just to do only the software. So simulation running has a defined society, different basically source available where you can get the idea how to do the simulations, where you get the much more information. So that will be available this open source centers. One is the Nano Hub, then Biomia campus, as well as community. So these are the basically source where I can get the idea about the simulation. So I think how much time there? How many time there? Hello? Hello?
Sir, are you connected?
How many?
Sir, you are not at all audible. Yeah, 10 minutes still left.
Okay. So this is basically the acknowledgement to my guides and IST shipports or prepare supports or doing the simulations. Also the Mithilesh Kumar Dixit in IIT Ahmedabad for providing software help. Also the higher authority in the college, Director Dr. Bozrul Haq, as well as the Director Mr. Sajal Ghosh of Principal Krishna Azra and Professor UC Kumar for constant support. And also thanks to the ATAL Academy for providing this share of work. These simulations, basically we are focusing on the composite materials and experimental works. We basically few speakers already say that, but in our presentations, I basically focusing on the molecular dynamic simulations and the finite element simulation that cells for all things.
Sir, thank you so much. Am I audible to you? Sir, are you connected?
Hello.
Yes. Sir, can you have the access of the chat box? You please check that a lot of questions have already arrived. Please check it.
Okay.
Just check from bottom to top. It will be better. There is a question from Ashish Thakur, I can see. Can you check this?
Ashish Thakur. 1 minute.
Sir, please turn on your video so that we can take a snapshot.
Okay.
Sir, can I read the question for you?
Yes, madam. I read the question.
Yes. Where is highest complexity parameters to be controlled observed in the nanocomposite modeling? How this typically integrates the continuum mechanics to predict behavior in the nanoscale reinforcement?
Actually, I am audible to me. Hello?
Yes, sir.
Okay, so continuum modeling and this molecular dynamics modeling is totally different. And continuum modeling, that means you have to basically in the bulk level property, but in atomic level, it is totally different. Where basically Newton's law you have to find two atoms. So here we cannot compare these two methods, molecular dynamics simulation and finite element simulations. These are the two different area. And yes, you can convert nowadays the molecular simulation model to continuum model. Show in my slides how to convert molecular dynamics simulations. It's much time as well as much cost for develop that models at the atomic level.
Actually, sir, your voice is breaking. I'm not sure whether your answer was clearly audible or not. Anyway, there is, yes, it is not audible actually. There is one more question I find from Arun Karthikeyan, sir. That is, how does the choice of interatomic potential influence the accuracy of molecular dynamics simulations in nanomaterial studies? Is the question.
Calculations, there is a force field there in the molecular dynamics simulations, and that force field is inbuilt because this inbuilt force fields automatically calculate the interatomic calculations or interatomic energy calculations. This energy may be repulsive or attractive. Is totally basically set up equations in the force field. No need to calculate this. You just choose the force field, and this force field automatically calculate all the interatomic calculations.
Okay, sir, there is one more question from Mr. John Alexis. Sir, is there any possibility to develop a new composite by simulation? Is there any work available for this? Can we do hybrid composite simulation? I think three questions were there.
In molecular dynamics simulations, to develop new composite, but it is basically in atomic level development. In real life, is it possible or not? It is not sure, but you can develop that new composite as well as hybrid composite also. Because nowadays new research area is going on hybrid nanocomposite where CNT and graphene both nanofiller will be added in the polymer matrix to get the much better property. So if you adding only graphene on the polymer material and if you adding the graphene and CNT within the polymer, you get the better property. And whenever mixing two nanofiller, it definitely a hybrid nanocomposite.
Okay. There's one more question. How does boundary condition selection affect stress distribution and defect evaluation in MD simulations of machining processes?
Yes, these very important questions. The boundary, whenever you have to find out the tensile property or compressive property or doing the any tribological functions, you have to set it's like a finite testing. So one, you have to give the fixed condition, other end you have to give the load. So in the MD simulation also, known as the constant condition, you have to set the constant in which direction the system will be moving. So there is the constant there, y-axis, z-axis, you have value of 0. Suppose you are moving the in x direction, so you have to give the y and z direction 0. So that way you have to give the constant or boundary condition in MD simulation. But in finite element, what will be there? You have to fix one condition, other condition you have to give the. So similar method, but in molecular dynamics, the term is known as the constant or apply the direction. What will be the movement? Movement is nothing but you have to change the atom velocity. So how you change the atom velocity? By changing the temperature. So you dynamic run, during the dynamic run, what will be there? Atom temperature will increase at the new velocity. That new velocity definitely move the directions, and you have to give the direction, in which direction it will be moving. So in the MD simulations is basically the force, that means you are adding some temperature so that the atom will. So in that way, basically we have to do the tensile testing, compression testings, or other simulation testing by changing the temperature and give the constant on that.
Okay, the next question is, have you considered the use of TFH solvent during simulation?
That is very important questions. In experimental work, whenever you do the experimental work in THF, what will be there? You mixing the graphene with the polyurethane. So after solidification, what will all the solvent will be evaporated. In the nanocomposite, no solvent will be available. All the solvent will be burned. That's the nanocomposite graphene and polymer mix. So no need for solvent. That's why we don't consider the TF solvent in the IMDC. Because this solvent has no functions. So there is very important. Don't compare basically consider the solvent during the composite discussion or composite simulations in MD simulation.
Another question is, can graphene be used as a nanofiller in polymetrics?
It's definitely graphene. We are using the nano to develop the polymer nanocomposite. So whenever you adding the nanofiller means graphene, TNT, even fluorine, so all are the basically nano. So if you adding the polymer, these types of nanofiller, definitely it will develop the nanocomposite. So nanocomposite means you are adding nanofiller. It may be graphene polymer, or graphene fluorine, or TNT.
Another question is from Vandana Shinde. Ma'am has written, how much percentage of discrepancy in properties of graphene is expected in simulation work?
That is, whenever you have to do the experimental work, and suppose 3 to 8% is graphene, so you get the better results in experimental way. But if you go to the molecular dynamic simulations, definitely a huge discrepancy. That means we have to not consider the void, because in OMD simulation we avoid all the void, but when experimental procedure, we always consider some effect or anything available in the material or samples. So definitely there must be a discrepancy, and but what will be advantage? We can get an idea which sample is better, how much weight percentage will be available to predict the property. So that idea we can easily done with the simulation.
No more question is seen right now, but there were a lot of appreciations from the audience end, and thank you so much, audience, for your active participation. But we genuinely regret the inconvenience caused because of the network. So I hereby announce the conclusion of the 5th day session. And we sincerely thank our esteemed dignitaries, speakers, and participants for their active participation and cooperation. And with this, the organizing team is signing off for the day, and we look forward to welcoming you back tomorrow at 2 p.m. sharp. Thank you so much, and good night to all of you.